Hello everybody, my name is Dr. Ahmed Bouchekhlal. So, engineers generally recognize two causes of voltage surges. These are classified as internal surges as they derive from changes within the system itself, or external causes which come from outside the system currently being affected by the surge. If you are looking for a surge protection device that delivers high levels of performance, the varistor technology may be the ideal solution. Today, I'd like to give you an overview of elaboration and investigation of centric temperature dependence of Zn varistor property. Firstly, what is the varistor? The word varistor is a combination of the words variable resistor, but unlike a variable resistor whose resistance value can be manually varied between its minimum and maximum values, the varistor changes its resistance value automatically with the change in the voltage across its making. It's a voltage-dependent, nonlinear resistor, or VDR for short. The varistor is used to protect the electrical and electronic system from a transient overvoltage. The current voltage characteristics of varistors are very similar to that of back-to-back Zener diode, which is used as a voltage regulator. Secondly, the Zn-based varistor sample with the nominal composition shown in this table was prepared by the traditional ceramics method. Raw materials were mixed by ball milling with zirconia balls and ethanol in the polypropylene bottle for 24 hours. The mixture was dried at 120 degrees Celsius for 12 hours and calcined in air at 750 degrees Celsius for 2 hours. The calcined mixture was pulverized to produce the starting powder. The powder was pressed into a disc of 11 mm in diameter and 2 mm in thickness at a pressure of 18 megapascal. The specimen was centered at 1218 for 2 hours, using a heating rate of 5 degrees Celsius per minute and was naturally cooled in the furnace. The resulting dark green ceramic bodies were approximately 10 mm in diameter and 1.5 mm in thickness. Silver paste was coated on both faces of samples, and the silver electrodes were formed by heating at 600 degrees Celsius for 10 minutes. The diameter of electrode was 5.8 millimeters. Characterization method. The surface of centered sample was observed by a scanning electron microscope equipped with energy dispersion X-ray spectroscopy. The average grain size of the nanograins D was determined by the linear intercept method given by this equation D equal 1.56 L per mn. The composition analysis of the selected area was determined by an attached energy dispersion X-ray spectroscopy, a DS system. The phase composition and the crystallinity of the centered ceramic were determined using an X-ray diffractometer, XRD. The DC electrical measurement at room temperature were measured using VE source measures. The current was recorded by increasing the applied voltage step by step manually to characterize the electrical field current density, e.g., behavior of the nano-based varistor ceramic. The nonlinear coefficient alpha was obtained from the equation alpha equal 1 per log V 1 milliampere per V 0.1 milliampere. The breakdown electrical field was measured at a current density of 1 milliampere per centimeter square, and the liquid current density was measured at 80% of breakdown electrical field. Thirdly, results and discussion. The XRD pattern of the nano-based varistor ceramics is shown in this figure. The XRD patterns reveal the presence of primary ZNO phase and a small amount of ZN2 MnO4 and a secondary phase will mate ZN2 SeO4 as detected by ODX analysis. This figure shows the SEM micrograph of the nano-based varistor ceramics, centered at 1218 degrees Celsius for 2 hours. The microstructure consists of a ZNO-gran as a primary phase and intergranular layer as a secondary phase. It's observed that the microstructure of the ZNO varistor ceramic appear more homogeneous with a finer distribution of secondary phases, lower porosity, and mostly a smaller ZNO grain size, with a more uniform size distribution. The average grain size D equal 3.45 micrometer. ODS analysis of secondary phase showed that in the sample which contain all oxides such as Zn, Sb, Cr, and Mn. This figure shows the electrical field current density, e.g., characteristics of the ZNO varistor. The varistor properties are characterized by non-homicity in the EG characteristics. It's clearly shown that the conduction characteristic divided into two regions, which are of a very high impedance in breakdown at a low field and very low impedance in breakdown at high field. It's found that the threshold voltage is 2065 volt per centimeter. The threshold voltage value is greatly influenced by the grain size and breakdown voltage per grain boundary. The smaller ZNO grain size and the higher VGB lead to high threshold voltage. The nonlinear coefficient is 20. It's derived from the EG curve and is controlled by the existence of an electrostatic barrier at the ground boundary. The results of electrical characteristics are summarized in this table. Finally, conclusion. The microstructure and electrical characteristics of sample were investigated. The ZNO-based ceramics reveal a complex microstructure composing of ZNO bulk grain and some secondary phases. The centering temperature plays an important role in the microstructure and the grain ground. Typically, the varistor ceramic centering in 1280 degrees Celsius exhibit admirable electrical property of breakdown voltage equal to 2065 volt per centimeter, alpha equal 20, and liquid current equal 0.23 milliampere per centimeter square. This ceramic could be applied to the nonlinear resistors for high voltage field.